Hello everyone. In this video, I would like to work an example of Prim's algorithm in L13-2. So here is the pseudocode for Prim's algorithm. We've been exposed to the pseudocode and we've also implemented this pseudocode in Python and ran Prim's algorithm on two different examples. One of those examples I want to work through in detail. So here's an example graph here that we want to find the minimum spanning tree of. Our starting vertex is going to be D. So our mission is to find the minimum spanning tree of this graph starting at D. So let's walk through Prim's algorithm step by step with D as the starting vertex. So according to Prim's algorithm, we're going to initialize all vertices distances to infinity, all vertices predecessors to 0. We're going to set the origin vertex's distance to 0. And then we're going to enqueue all vertices into the priority queue unvisited queue. So let's take a look at our initialization for this algorithm. So initially, all of our vertices, A, B, C, D, E, F, G, their predecessors are set to 0. And our starting vertex, D, has a current cost of 0. Now we enqueue all of these vertices into our unvisited queue, and we see at the front is D0, and then all of our remaining vertices with infinity as their current costs. So we're ready to start going through the while loop of Prim's algorithm. So while the unvisited queue is not empty, we're going to dequeue the highest priority item in unvisited queue into a variable called curvy. And then we're going to look at each adjacent vertex, adjacent V of curvy, to see if we have a new smallest edge weight from curvy to adjacent V. If so, then we're going to update adjacent V's path distance to new cost. This is our attribute. We're going to set its predecessor to curvy, and then we're going to update adjacent V's location in our unvisited queue with its new higher priority, because we found a smaller edge that connects to this adjacent V from curvy. So let's get started. So here's our initialization code, and we're going to dequeue from the front of the queue, which is D0. So here is D here. Now for each one of the adjacent vertices of curvy is D, we're going to see, do we now know about a smaller edge weight that connects into this vertex than we've previously seen? And the answer for all of these connected vertices, A, B, E, and F, is going to be yes, because their current cost is right now infinity. So we're going to process, let's say, A first. So A's predecessor is going to be set to D. A's priority is going to be updated from infinity to 5. B's predecessor is going to be set to D. B's new priority is going to be set to 9. E's predecessor is going to be set to D. E's priority is going to be set to 15. And F's predecessor is going to be set to D. And the new priority is going to be set to 6. So here is our order. We have A5, F6, B9, E15, and we have not discovered C or G yet. So let's move on to our next step. We're going to dequeue from the front of our queue. So we're going to dequeue A5. So we are now going to add the edge to our minimum spanning tree, AD, with weight 5. And A is now our curvy. So let's take a look at all of the vertices in the neighborhood of A, those that are adjacent. So we've already processed D, so let's take a look at B and see if we have found a new minimum cost or an edge connected to B. And we do. So previously our connection to B was 9 from D. Now we're going to update that to 7 from A. So B's priority is now 7. And we've processed both of the adjacent vertices of A. So now, and here's the example here, B's predecessor set to A. So now we're going to dequeue from the front of the queue, F with priority 6. So now we're going to add the edge DF to our minimum spanning tree. And we are going to process all of the adjacent vertices of F. So let's start with E. So previously, E's predecessor was D, and the priority was 15, which was quite high. We found a new shorter edge to connect to E, which is 8. So we're going to update E's predecessor to F, update E's priority in the priority queue to cost of 8. And now let's take a look at G. We have finally encountered G. This is the first time. So no matter what this edge is, it's going to be a lower cost than infinity. So let's set G's predecessor to F, and we're going to set the priority in our priority queue for G from infinity to 11. So here's our order now. Let's dequeue from the front to dequeue B7. So now we're going to add the edge from A to B with weight 7. We're going to process all of the adjacent vertices of B. We see from B to 9, but we've already added D to our minimum spanning tree, and this would create a cycle. So we're not going to do any updates with regards to D. We already have a shorter connection through A. Next, let's process C. So this is the first time we've encountered C. Previously, its priority was set to infinity. Now we're going to set it to 8 and set C's predecessor to be B. And now let's take a look at E. So previously, our priority or our cost associated with E was 8 through F. But now, if we connect to E through B, then we're actually going to have, through B, then we're actually going to have a lower cost. So we're going to update E's predecessor from F to B, and we're going to update E's priority from 8 to 7. Next, we're going to dequeue from the front of the queue, and E kind of pushed its way up to the front here, and we're going to dequeue E7. So now we're adding this edge from B to E. We're going to process all of the adjacent vertices. So let's take a look at C. So previously, C had a priority of 8 through B. So we're going to update C's predecessor from B to E and updates its priority from 8 to 5. We're going to take a look at G. So G's priority was previously 11 through F. So we're going to update G's predecessor to be E, and we're going to update its priority in the priority queue from 11 to 9. And then we're going to take a look at F. We've already added F to our minimum spanning tree. A shorter connection was made through 6. So we are going to not process or make any updates with regards to F. Now we're going to dequeue again from our priority queue, and we dequeue C5. So let's take a look at C5. That adds the edge to our minimum spanning tree from E to C, and there are no neighbors to process here because we have already added B and E to our minimum spanning tree. So next we're going to process G9. So that's going to add the edge from E to G to our minimum spanning tree, and all the adjacent vertices of G, E, and F we have already processed. So our minimum spanning tree is complete now. Our unvisited queue, our priority queue, is empty, and that is the stopping condition on our while loop's Boolean condition. So we are done. Here is the minimum spanning tree. So F to D to A to B to E, and E connects C and G.